Niels Bohr, born 1885 to 1962. He is a Danish physicist. Bohr was an active participant in the early development of quantum physics, mechanics, and provided much of its philosophical framework. During the 1920s and 1930s, he headed the Institute for Advanced Studies in Copenhagen, where many of the world's best physicists came to exchange ideas. Bohr was awarded the 1922 Nobel Prize in Physics for his investigation of the structure of atoms and of the radiation emanating from them. Bohr has four basic assumptions. The first assumption is the electron moves in circular orbits about the proton under the influence of the Coulomb force of attraction. The electron occupies only orbits with certain or fixed radii, which it represents in figure 28.5. So what is this Coulomb force of attraction? Coulombic attraction is the force of attraction between positive and negative charges. If the charges on the particles have opposite signs, the force will attract, and if the charges on the particles have the same signs, the force will repel. The second assumption is only certain electron orbits are stable and allowed. In these orbits, no energy in the form of electromagnetic radiation is emitted, so the total energy of the atom remains constant. The third assumption: radiation is emitted by the hydrogen atom when the electron jumps from a more energetic initial state to a less energetic state. The jump can't be visualized or treated classically. The frequency of the radiation emitted in the jump is related to the change in the atom's energy given by this formula. The EI minus EF is equals to HF, where EI is the energy of the initial state, EF is the energy of the final state, and the H is the Planck's constant. The frequency of the radiation is independent of the frequency of the electron's orbital motion. The fourth basic assumption: the circumference of an electron's orbit must contain an integral number of de Broglie wavelets. The electron can exist only in certain allowed orbits determined by the integer n. Ground state, lowest energy state, and corresponds to N1. The uppermost level shown, corresponding to E is equals to 0 and N to infinity, represents the state for which the electron is completely removed from the atom. In this state, the electron's kinetic energy and potential energy are both 0, which means that the electron is at rest infinitely far away from the proton. Ionization energy, the minimum energy required to ionize the atom, that is, to completely remove the electron. This figure is an energy level diagram for hydrogen. Quantum numbers are given on the left, and energies in electron volts are given on the right. Vertical arrows represent the four lowest energy transitions for each of the spectral series shown. The colored arrows for the Balmer series indicate that this series results in visible light. Bohr's correspondence principle. In our study of relativity, we found that Newtonian mechanics can't be used to describe phenomena that occur at speeds approaching the speed of light. Newtonian mechanics is a special case of relativistic mechanics and applies only when velocity is smaller than speed. Similarly, quantum mechanics is in agreement with classical physics when the energy differences between quantized levels are very small. This principle, first set forth by Bohr, is called the correspondence principle. Hydrogen-like atoms. The analysis used in the Bohr theory is also successful when applied to hydrogen-like atoms. An atom is said to be hydrogen-like when it contains only one electron. Examples are singly ionized helium, doubly ionized lithium, and triply ionized beryllium. The results of the Bohr theory for hydrogen can be extended to hydrogen-like atoms. Although many attempts were made to extend the Bohr theory to more complex, multi-electron atoms, the results were unsuccessful. Even today, only approximate methods are available for treating multi-electron atoms.